This is the first podcast dealing with chemical kinetics. This is the area of chemistry that concerns reaction rates and reaction mechanisms. Now, chemical kinetics is really supposed to be a calculus-based subject in chemistry. So keep that in mind as we go through the rest of the kinetics, that we're really trying to understand and learn kinetics without necessarily doing the calculus that's involved with it. Now, in order to begin a study of chemical kinetics, it's important that you understand what reaction rate is. Reaction rate is the change in concentration of a reactant appearing, a reactant being used up or a product appearing per unit of time. So if you look at the fraction there, rate is equal to the concentration of A being some substance at time 2, and then minus the concentration of A at time 1, and then that's all over the change in time. Now this should almost look like a slope kind of formula to you, and then it's summarized there. Rate of the substance, either appearing or disappearing, is the change in concentration of A over the change in time. Now if we took a look at a specific reaction, this is 2NO2 gas going to 2NO gas plus O2, and then the concentrations of the substances have been graphed over time. If you'll notice, the NO2 is decreasing, that's the green on the screen. The NO is increasing, and the O2 is increasing. Notice that the NO is increasing twice as fast as the O2 is. So we can measure the disappearance of reactants, so that would be the NO2. We can measure the appearance of products, so that would be the NO and the O2 on the graph. And then, as I said before, they're proportional stoichiometrically, so you can use the balanced equation, and again, the NO is going to appear twice as fast as the O2 appears. Now, we can also, at a particular point on one of the curves, we can take a line that is tangent to that point and calculate the slope. That slope then gives us the change in concentration of that substance, NO2, over the change in time. So it's a slope-based function. We can also take a look at the change as the reaction proceeds, as long as the reaction rate is dependent upon the concentration of that substance. So we will encounter reactions where the concentration does not affect, the concentration of a particular substance does not affect the rate. Now, we are going to take a look at two different rate laws. They're calculated from different kinds of data. However, they arrive basically at the same idea. We're going to start with the easiest of the two, and that's the differential rate law. This is a relationship between the concentration of reactants and the rate of the reaction. So we're going to basically ignore the products per se and just take a look at the reactants. This particular rate law, the differential rate law, is the one that's usually just referred to as the rate law. When we talk about the integrated rate law, we specifically call it the integrated rate law, and that's the relationship between the concentration of reactants over time. Now, when we write a differential rate law, we would be given data like you see here on the screen. And that data then would be utilized to determine the overall order for the reaction. And we'll show you what the overall order for the reaction is going to look like and how to write a rate law. But this is what your data would look like. So you get the concentration of the two reactants, the NO and the Cl2, and you'd get the rate. And this particular experiment was done 4 different times using 4 different concentrations and then getting 4 different rates. To determine the rate law, keeping in mind the rate law is the differential rate law, you determine the values for the exponents in the rate law. And remember, we're only dealing with the reactants. And there is a constant in the rate law. So the K is the constant, NO raised to the X power, Cl2 raised to the Y power. And our job is to determine the value of X and the value of Y. Now, in experiment 1 and 2, Cl2 is constant. And if you look at the rate there, the rate appears to, and the NO concentration doubles. So the NO concentration is going from 0.25 to 0.5. The Cl2 is constant. And then take a look at the rate there. What happens to the rate of the reaction? If you do the math, the rate of the reaction actually quadruples. When you have a doubling in concentration of a reactant and the rate quadruples, that means that reaction is a second order reaction with respect to the substance that's changing concentration. So it's going to be second order with respect to NO. Okay, so we can substitute then the 2 in there for the x. So we know the exponent there for NO is a 2, so it's squared. Now we can do the same thing with Cl2. Experiment 2 and 4 there, if you look, the NO is constant, so that means it's a non-factor. So if we look at the concentration of the Cl2, how it changes, it goes from 0.25 to 0.5, so it appears to double. And then if you look at the rate there, the rate appears to double. So we have the Cl2 concentration doubling, and then we have the rate also doubling. So this reaction then would be considered first order with respect to Cl2, because whatever happens to the concentration, the same thing happens to the rate. Now, once you have the rate law written, and you'll see it there at the bottom, rate equals K NO quantity squared Cl2 to the first power, then the next step is to determine the rate constant. And that's the K value that we're looking for. And literally you just do this through substitution. So you take one of the experiments and you substitute in the rate, the 1.43 times 10 to the negative 6th for R. The K is what we're looking for. We're going to plug in the NO concentration for this experiment, which is 0.25. Square it, because we determined the reaction is second order with respect to NO, and then we're going to plug in the Cl2 concentration, which is 0.25 in this particular experiment, and we're going to raise it to the first power. So we want to calculate that K value, and you can see in the box then the K value ends up being 9.15 times 10 to the negative third. And then if you look at all the units there, when you look at the units mathematically, and algebraically, you end up with an L squared left on the top, a mole squared left on the bottom, and then a seconds left on the bottom. So these rate law constants do have units on them, and the units are important. Now you would do this then for all 4 experiments, and then you would average the 4 to have an overall average K value. And most of the K values should be fairly close to each other, but you do them for all 4 experiments, just like we did here on the screen, and then you would average all 4 of them. So, thirdly then, you determine the overall order for the reaction. So here's our rate law, which we calculated. The overall order for the reaction then is a sum of the exponents. So in this particular case, we would take the 2 from the NO, the 1 from the Cl2. That would give us a total of 3. So overall, this reaction is a third order reaction. Okay, so that's a brief introduction to the differential rate law. We also are going to create a podcast which shows you how to determine those exponents mathematically. All right, so we'd like you to be able to do it kind of qualitatively, looking at the data, and then more mathematically.